functions of several variables. And we have been talking about limits and continuity. So once again, the key is the complexity of the issues right here. In comparison to the numerical functions, you can approach a particular value of the input in an infinitely many ways. So, well, there's another one. Clockwise, counterclockwise, it doesn't matter. So, in that example that we saw, it was especially important because it actually indicates the limitations of the coordinate y or variable, one variable time approach. Okay, so the function might behave this badly, and yet it would look entirely innocent as far as the two variables are concerned. You go along the x-axis, along the y-axis, it doesn't matter. It looks all looks good, but the reality is it's not. So the limit doesn't exist. Vice versa, it does work. So it works in one way. If it works this way with the magnitudes or distances. This one. So this is what we how we understand limits is that once again the distance xn a goes to 0. So in that picture here, you can certainly think in terms of these distances. Say the distances from the xn over here to and this distance gets shorter and shorter and shorter. So that's the convergence as we understand it. Okay, so and then we take all the sequences, all possible sequences, produce the same behavior, which is this. Okay, and it converges to some number. So that if that works out, then we can just say, well, that's okay. We can only we pick one with respect to any variable. One variable it will do. Okay, so that's the biggest thing here. But on the other hand, everything else works out very nicely in comparisons. Once you go through the difficulty, the theorems all hold. The algebra of limits are all applicable. So in comparison to the limits of the algebra limits of parametric curves, you can notice that we have once again we have these two extra items. Because the output is number, we can divide it along. Okay, so that is the example. The function is specific. I just talked about it is a very specific function, so I didn't make it up. And it looks quite I'm sorry, not this one. The specific function is here somewhere. Yes, this one. Okay, so it looks quite innocent. Okay, so limits are then all the rules applicable. We're not going to spend any time looking at that. So just all the rules in the same manner as with the rules of limits of numerical functions. It's still fully applicable. You work in the same manner. And in fact, just remember that rule once again. You don't really the nature of the computation you carry out doesn't matter as long as the rules apply and as long as every expression in the sequence makes sense. The whole thing makes sense. Okay. So the last topic is continuity. So it certainly can be explained once again in that in informal way as continuity is explained as a small change of the input produces a small change of the output. Okay, so that's a verbal description which applies to all functions of any nature. But whenever you test it, that idea, the easiest way is just to test it within the calculus 1 environment. So you test it. I mean, you have to understand that. To see that you understand it properly. This is a function that this rule fails. So small change, if I deviate very little off this point over here, my value of the function jumps from 0 to 1. Okay, so that's this continuity for you. All of those are examples that you saw of discontinuity in Calculus 1, including jump, removal discontinuity, and infinite discontinuity, or all kinds of wild behaviors, including this one. They're still applicable. I mean, every function of one variable can be made into a function of two variables in a very simple way. So if I have a function y equal, or z is equal to f of x, well, let me make clear that this is a number. Okay? So if you see something like that, and this x is a lowercase, who is to say that this is a function of two variables? I mean, you can say that it is of one variable or two. It doesn't matter. It could be the same formula. For example, y equal x squared is the function of two variables or of one. Well, it is up to you depending on the context, and pretty much it's your choice. Okay, so then that's the idea of why all of the bad examples of bad behaviors are still applicable. Differentiability will be slightly more complicated. Once again, different directions will produce different outcomes. So that is the continuity, which is for the most part helps us with the limits, easy to compute just simply by substitution. Which is, so this is treated or explained as the substitution rule frequently, even though it is silly to apply the word rule to the definition, but that's just how it works. Sometimes easy to remember. And then there are some global properties of continuous functions. Well, actually, the algebraic properties of continuous functions first, and that is from those four properties of limits. These four, everything follows the same about continuous functions. So the sum of two continuous functions is a continuous function. Constant multiple product as well as the ratio of two continuous functions is continuous as long as the function is not equal to, the denominator is not equal to 0. So if I want to write it out, so suppose it is pretty much the same, restating the same four facts, but in more narrow sense. So suppose y is equal f of x, y, and z equal to g of x, y are continuous at xy equal ab, and certainly it's applicable to any other dimension, any number of variables. Then number one, f plus g is continuous once again at that point, and cf where c is a real number. And f times g, and fourthly, f over g. So once again, let me repeat the last one requires some extra words. So f over g is continuous at xy equal ab, provided the g of ab is not equal to 0. Okay, so because the limit has to be equal to the value, so the value at the very least should not produce division by 0. So that's why the extra condition here. Okay, otherwise we are in very much the same position as with numerical functions. Meanwhile, the global properties are important just like they were in Calculus 1. Global properties meaning such as global properties as well, every continuous function defined on a bounded closed interval bounded closed set, I'm sorry, is bounded. Okay, so So that is a very important rule. The only thing that remains to be, well, first of all, let's remember what it means in calculus 1. In calculus 1, it meant very simple things. So the closed-bounded set was simply an interval that we would limit ourselves to. Okay, so if you have a function defined on such an interval, then and it is continuous, then this piece will be bounded. And if it is bounded, then the conclusion is that it attains its maximum minimum values. So all the optimization problems then can be solved. They have solutions, right? Okay, so we're going to do optimization problems with a function of several variables as well. So that's why we need this result to make sure that the problem we're trying to solve actually has solution to begin with. So that is Calc 1, numerical functions. And like I said, so every continuous function defined on an interval AB with endpoints included is bounded. Okay, so it doesn't go to infinity, and that's why you can also proceed to the next theorem and say that there is the maximum or minimum point is reached. Okay, as you can see, there is one. It is not. No trouble to explain what bounded set means in the multidimensional space, but the last one, the closeness, might require a little bit of work. So what we're talking about here is now proceeding to calculus 3. We have a surface once again. Boundedness, however, is understood in the exact same way as before. By which I mean that the values are limited from below and from above. So values of the outputs. So in other words, f of xy, if it's a function of two variables, less than or equal to some q, real number. So that's f is bounded. That's the meaning. The meaning of a function being bounded is that is literally those numbers. The output are still numbers. So what it means to have a bounded set is clear then. Okay. So that's the conclusion. Okay. We have two words bounded. So I did the last one. So bounded. This was I was talking about the function being bounded. But then I have bounded over here the boundedness of a set in R2. So over here in R2. So I'm talking about the part of the domain of the function, and once again it has to be, as I said, bounded and closed. So bounded is not very hard to define. So a set in R2 is bounded when, say, xy, the magnitude of xy is less than, say, qp or something. In other words, real number. In other words, it doesn't go to infinity. That's all there is. Reach xy in the set S. Okay, so some functions, so some sets are bounded, some are not. So say x's are unbounded. Okay, so x's are not. Circles are. Squares. Well, you can think of anything as long as you can. It doesn't matter how wild that thing is. If you can put it in some kind of circle, even a large circle, it makes it bounded. This is bounded. And you realize that with this notation, we can explain bounded set in three-dimensional space, four-dimensional space, any dimensional space. One thing didn't come up before, but certainly it's worth thinking about is boundedness. You have a parametric curve. A parametric curve lives in the multidimensional space, And you can ask yourself, is it a bounded curve? And the meaning is the same, so whether or not it will at some point go to infinity or it will stay within a certain sphere. Okay, so that's the boundedness of a set, and we certainly cannot expect the function to be bounded on an unbounded set, right? So the surface certainly can just go up, up, and up, and up. The last one, the last concept here is closed sets. Okay, so it is an analog, just like boundedness of a set is an analog of this. A and B is bounded. A and B are numbers, so they are not infinite. But now we're not living in R anymore, so that's what we did on the x-axis, and the only interesting set in that respect was an interval AB with endpoints included, and this was described as a closed interval, right? A closed interval, and but now we have just so much variety, and just starting with examples. So what closed means? So a closed set in R2. Okay, so first, first, those that are not closed. As a contrast, or let's do closed. Closed. The point of a closed set is that it includes its boundary, whatever the boundary means. So this set is, I describe it as it's not a circle, it's a disk. A disk, closed disk. Closed disk, which means that it not includes only the circle, but also what's inside. I write it as, how do I write a disk of radius 1?
X squared plus y squared is greater than or equal to 1?
Less than or equal to? Less than or equal to 1, indeed. So xy, that is my disk. So when it is equal to 0, we have a circle. When you have less than or equal to 0, it is a disk, a closed disk. Okay? Now an open disk is almost the same, so it's also a circle, and it includes all what's inside, but it does not include the boundary. Okay? So the equation is, the definition of this set will be strictly less than 1. Okay, so that's how we exclude the boundary. We exclude excluded x squared plus y squared is equal to 1. That's our circle, and it is excluded from what we had on the left. Okay, so what it is these are just examples, so they're not easy to explain. They're explaining things, but really not telling us a lot. And so you need the definition. So how do we define it? How do we make it specific that it does not include this boundary? And the way to put it is to use limits. So this is the definition. So S is in R2 is closed when every conversion sequence in S has its limit in S. Okay? This is why it is not going to work here. I have a sequence, and it is convergent. It is convergent. This is the limit. This is the limit, but it does not belong to the set itself. Okay? So you can imagine that if I have a sequence here and it converges, then there's no way for this limit to be anywhere but inside on this of the circle, including the boundary. Okay, but it is likely that you can, if you take intermediate steps, you can reach the boundary and in such a manner with a sequence, and then turns out that on the right, when the set is not closed, well then that set is not does not contain that limit. Okay, so and that's the key why the condition of what we're pursuing, we want to conclude this, that the function is bounded, and then it attains its maximum minimum values. So the continuity of the function is given, but where the function resides, or its domain, is what we are trying to understand now, and this is the definition. So once again, closeness being the condition of where the limits of all the sequences belong. It is the definition might be slightly. It is certainly a new kind of definition in comparison to calculus 1 especially, but easiest to understand through examples. These two are the main examples, so you can also think what's happening in 3 dimensions. Instead of a disk, you have a ball. Once again, you can exclude the sphere, which makes it not closed. And but there are others. For example, there is more room for in terms of dimensions. So, for example, this is a well, first of all, there you could have only part of the boundary might belong to the set. That would be one example. Still bad. So a rectangle which includes its boundary is fine, it's closed. But if it excludes one single point of its boundary, including this, I could exclude this point, and then it's not closed. Okay, so once again, these are not closed. This is not closed. Okay, so you take the line or segment, exclude one point. Once again, it's not closed. Just think about it. Is there a sequence? There is a sequence. You can't find a sequence converging to that point that you just threw out. So it's not closed. All of these are not closed. Most of the time, it is, practically speaking, what we're going to be dealing with is some kind of rectangle or a circle, but rectangle most of the time are good. So a rectangle like that, this one is closed. Okay, and we take it from there. And so on a rectangle, or in dimension 3, some kind of box, the maximum value will be attained, and so some kind of maximization problem will be solvable. Even though you can imagine that there's some weird. You might remember problems in calculus 2 integration, and you may have integrated functions on some kind of weird domains, including like a parabola cut out by a straight line, and then this is pretty much you did integration over this region. Okay, of this region to find its area. So it could just as well be the part of the domain of the function. So, but as long as you include the curves themselves, it will be closed. So this is closed. So once again, the conclusion then holds. The global maximum minimum points are attained. So then we will be able to apply all the derivatives. We're going to learn derivatives and then apply derivatives to maximize problems to functions looking like this. So of function of 2 variables, and it won't even matter in any dimension. It will be fully applicable. All we need is the derivatives. Okay, so well, a couple of more theorems. And once again, referring every time to a familiar theorem, hopefully from calculus 1. And this one is, the next one is the intermediate value theorem. Okay, so what is the intermediate value theorem from calculus 1?
If f is continuous on, say, the closed interval AB.
Okay.
And if f of A is equal to
yeah.
say K,
Okay.
and f of B is equal to J.
Okay.
And I guess we have to know what kind of direction, what kind of interval Kj or Jk is, so we'll just assume that, I guess I could have just said f of A is greater than f of B. Sorry.
Yeah, we don't really need it necessarily. We can use the word between instead. It is intermediate. So between these two values, these are the values. Okay, and what we're saying is that the intermediate value between them, between those, also is taken care of by the function. Okay, so that's this is the f part, and then for every intermediate value, so say d between k and j, there is a c in a b such that f of c is equal to d. A, B, J. Okay, so these are the two values. Let's assume that the function is continuous, but we don't know anything about it, so some wild stuff is happening. Okay, then what we're saying is that we pick a value d between k and l, anywhere else, and we can trace our backwards. That's the thing about we are computing functions directly like this. From a, I'm going to k. From b, I'm going to j. Okay, and now we pick d between those two, and we're going backwards to find the source. And there is a source. Okay, so in other words, as we're going horizontally over here, we're not going to miss the curve because the curve is continuous. That's what you would expect from a continuous function. So if you cross it with a horizontal line appropriately chosen, it will not miss it. It will hit that point, and that's how you can retrace your steps and find that C, the input for this output. So the output is given D, and we want to find D when there is such an input. Okay. So now the trouble is certainly is to generalize, because even though the vertical axis, the output axis is the same, right? The functions are real valued. The trouble is here. The input is now two-dimensional. So you have x, y, and z, and so you could still start with two values, k and l, k and j of the function. However, that's not going to help us a lot with where we should be finding that d. So let me try to plot what the graph might look like. Maybe like this. Okay, so that's the graph, z equal f of x, y. Okay, then we're trying to start the same way. We take two values. Unfortunately, there are no endpoints of our interval. So even if I chose just for simplicity, let's suppose the domain of our function is a rectangle, then where are there are no endpoints. So just picking two endpoints, 2 points are here and there, say this is A and this is B, that doesn't really help, even though we're not going to bring those values here, so f of A, f of B, but how do we know, can we conclude, we can't conclude that there's a value between them. There is, however, a different way of looking at it. Even though I think it is plausible, I think it is plausible to try to generalize this this theorem by taking the values, say A and B, we make them capital. So instead of A lowercase, B lowercase, we would take two values, capital A and B, and choosing them on the boundary of the domain. Okay? So domain is closed and bounded, and AB belongs to its boundary. Unfortunately, we didn't really explain what the boundary is. And then we take those two values. G is equal to f of A, k is equal to f of b, any 2 points, then if you think about what the graph looks like, it is a surface. Okay, so what do we do to the surface to bring it to the z-axis? We just push it. We just push it horizontally or wrap it around. Yeah, I guess you can say that. We can take the surface, which is a piece of cloth, like hanging, and then to find that's the graph. Okay, but then to find the image, which is what we're talking about, the image. An important concept here. This is the image, and this is the image of our function, either one or two variables. So how do we produce the image from the graph? We push the graph to the horizontal. If we push it down, we get the domain. Okay, that rectangle over there. If we push it horizontally towards the z-axis and wrap around that piece of cloth around the z-axis appropriately, that will give me the image. And then we're saying that no point on the image will be missing, so there will be no gaps, which is kind of makes sense. So that's one. I guess I'll just leave it here. Just give you the idea of what how things still reappear. Continuity produces similar results to those from calculus 1, even though the domain becomes much more complicated. So we can say that. Well, we can actually say that, well, suppose the domain is a rectangle, okay, and then the image is, so let me put it this way, so if the domain is the rectangle, then the image is what? Look at the picture. So this is the domain, and this is the domain now. They are different, right? So we replace the domain being an interval to domain, well, I don't want to write this, to domain being a rectangle, but the image is the same. The image is an interval, right? The image, either way on the vertical axis, is in either case it is an interval. And that's what is so special about intervals. They don't miss points. So every point between 2 points in the interval, you pick one in between, it is still there. Okay, so every single point within the domain is then within the image will be taken care of without gaps. So no gaps in the image. That's the short version.
To find our C in the multidimensional case, are we just so I know what the picture? Are we imagining like that? Say the absolute the distance from A to the origin was greater than B. Are we saying that we imagine like a circle with radius A and then a smaller circle with radius B, and that the
Wait, related to this problem?
Yeah.
There is no method for finding C, really. Well, there is, if that's what you're referring to. It is a, what's the word? Bisection.
Oh, okay.
You keep cutting it in half,
Okay.
and you see whether you higher or lower the value that you're looking for. Okay, and then by bisection, that sequence will converge to C. Now here, following your logic, it's not going to be a circle. You're going to take that rectangle and start cutting it in half.
Okay.
And then once again see which side you are, and once again cutting horizontally and vertically, one at a time, will also converge you to C somewhere, say C capital here somewhere. Okay. So, but basically the conclusion there will be no gaps in the image of a function of two variables, just as, I don't think we discussed that at all, that with parametric curves the same story is true, but it was just so, seems kind of obvious. If the parametric curve is continuous, then of course there will be no gaps in its path. Okay, so still applies. Okay, so maximum minimum points. extreme value theorem that can be solved now under those circumstances. And now we're moving to towards the derivative finally. So we did all the preparations, and one preparation is discussing what. So preparation was slopes in different directions. Okay, and secant lines. Then altogether it gave me secant planes, right? And then planes altogether that we looked at, representation of a plane in a particular way using the dot product. And finally limits. So we need to, what the derivative? Okay, for the derivative, for all of these things we need. Let me once again draw this triangular diagram to see how we progress from calculus 1. So once again, calculus 1, numerical functions. And we have the derivative now. I just take f prime of a is equal to limit x goes to a f of a plus f of x minus f of a over x minus a. So we will stick to the definition for some time, definition of the derivative at one point at a time. Okay, so that's the definition from calculus 1, the meaning of the derivative of a numerical function. Now I'm moving on to parametric curves. Okay, so f prime of, say, a, again, once again, capitals are multidimensional, lowercase are numbers. So it is still a limit. So I'm trying just rewriting the same formula as I have for numerical functions, just using the different letters as well as the different capital versus lowercase, uppercase number for numbers and vectors. Okay, so it will be f of t minus f of a over x minus a. I'm sorry, over t minus a. Okay, so that was the definition of the derivative. Derivative at a. Everything worked out because the numerator is a vector, but the denominator is a number. So dividing by a number, say multiplying by a number. So this is nothing but a vector algebra. Subtracting two vectors, then dividing by a number, and then finally taking the limit. Okay, and that limit was this limit was a vector limit. And now if we try to do the same with functions of two variables or more, then if I just try to write out as we have f prime of a. Remember now the input is multidimensional. I have the limit x goes to a. So far so good. We know how to do these limits. Just talked about it. The numerator is f of x capital minus f of a. So far so good. One number, another number, subtract. Now, what about the denominator? What? Any comments about the denominator?
Vector.
It's a vector, right. It's a vector. And so, okay, if it's a vector, then what's the conclusion? The numerator, by the way, is a number. So, let's divide a number by a vector. What does that produce?
Still a vector.
No,
Yeah, we can't, I mean, we can't do that.
can't. It doesn't produce anything. It is totally, unfortunately, it's just totally meaningless. So we just have to cross it out. It doesn't work. So that is the main reason why we study parametric curves before functions of two variables, because derivative, that's calculus, and derivative is very easy to define. No change whatsoever as far as the algebra is concerned for defining the derivative, and yet functions of two variables doesn't look that much worse. It just does not work. Okay, so one way, and I want you to consider this for a moment, alternative. So how do I fix it? Let's try to fix it. How do I fix it? I cannot divide by a vector. What can I try to do?
Use maybe the vector's components.
Yes. Yeah, that's not what I'm driving at, but yes. And that is, will produce partial derivatives. Right. But I was driving at something else, and that is, if I cannot, well, first of all, components, so it's a legitimate way of approaching the problem, except it will, you have one derivative per variable. Okay, so, and then we have to recombine them together to have the derivative, which is what we're talking about here. What is the derivative of a function of two variables? So I just combine somehow from the partial derivatives. So that's the word partial, after all. So one way to try to fix it is to divide not by a vector, but by a number. Where is there a number here visible somewhere? How about we take the magnitude? So that's not a bad idea. It still totally fails though, but we're going to use that later. It fails in this environment, and why does it fail? Because well, there's a very simple reason why this limit might not exist. Most likely, it's not going to exist. So what we just saw is just even with let's try to examine very quickly why this is not working out. If I just take my example of a linear function once again, as we have, say, x plus 2y. Very simple linear function. The derivative, there is no limit, no worrying about the limit, right? That's what linear functions are for. They approximate everything, and so without limits. Okay, so then if I'm looking at f prime of, and say a is equal to 0, okay, so then what is that I'm computing here? F prime of 0 is 0 being 0, 0. I throw out limit. I have x plus 2y minus 0 divided by the magnitude of x plus 2y. Okay? Or that is gone. I have x plus 2y over x plus 2y magnitude. I'm sorry. I'm sorry. I messed up the denominator. X is xy, so it's just the magnitude of xy. Magnitude of xy. So over here it is x squared plus y squared square root. Okay. So once again, it might not be obvious, but let me put the 0 here, 2, 0, 0. So the derivative computed through the magnitude of the distance. So in other words, it still makes sense if you think about it. We're talking about the rate of change of the value of the function, the numerator, over with respect to the rate of change of the input, x minus a, except we're looking only at the magnitude, not actual change, but the magnitude. It's like looking at the distance rather than displacement. Okay. So can you see what this problem might be, or this function might be a problem? That's from discussion from yesterday about limits.
I'm guessing that not every sequence leads to the same limit, right?
That's right. That's right. In fact, you can, that we had to work hard yesterday to find that bad direction, because x and y were okay. But here, if you just go along the x-axis or along the y-axis, you're gonna already produce two different results, right? So along x-axis, this is 1. Along the y-axis, it's 2. So yeah, the slope is different in different directions. Now we know that. So if we try to kind of combine them into one number, it's impossible. So the derivative of a function of two variables cannot be a number. because as we know, once again, two different directions or more directions, at least two directions you have to take into account, and one number won't do it because different directions will produce different numbers, and they will match. The limit doesn't exist. Okay, so so we roughly know what the answer should be. Remember those approximations that we did. Along the we cut the graph vertically along the axis, along y's, and look at the slopes in two different directions. But once again, it is a coordinate one, coordinate y analysis. Another way is to look at something entirely different, and not entirely different, but rather something familiar from before, and that is linear approximations. So not trying to compute it right away, what the derivative is, but rather understand linear approximations, and then the meaning of the derivative will fall into our lap. Okay? So linear approximations, we certainly, in calculus 1, you proceed with f prime, and then you proceed to linear approximation. Okay, so remember the meaning of the linear approximation in calculus 1. So y equal f of x at x equal a linear approximation is, or well, the technically is best linear approximation. What is it?
Y equals f prime of a times x minus a.
X minus a plus f of a. Okay, so even though this is the linear part, right, really, this is the only part we care about. So that's how we went with the numerical functions, because we can compute the derivative as the limit, and so we took that route, and then we got to linear approximations. But there is but then when you start looking at the approximations, you can describe linear approximation by property. And in other words, you look at all linear approximation and then understand what makes this one the best one. Okay, so linear approximations are what are they? Y equal mx minus a plus f of a. So in other words, we're looking at at what second lines pretty much. So all of these they're passing through that point, okay, a f of a to begin with, but then the slope varies. If you look at it, they are approximation. They're linear, number one. The two, they are kind of approximating the function but not at its best. We know that the answer is of the best linear approximation is the tangent line, but what makes it the best is the following limit. So best is the limit. Let me put here y equal L of x. I want to emphasize that linear approximation is approximation with functions. They just happen to be linear. And in calculus 2 you saw quadratic approximation, cubic approximation, and so on. So what makes the best linear approximation is f of x minus L of x divided by x minus a absolute value. X goes to a is equal to 0. Okay, so that is the property of a linear approximation, and it might remind you of things about Taylor polynomials. And now what we're gonna do with it? That's the idea. We're just gonna replace absolute value with magnitude, and we are free home. We can have linear approximation of functions of Taylor.